Hello, today's topic is on energy of simple harmonic oscillator. So let's just get started. So we remember that any SHM is always characterized by, I've always taken an example of a spring. Let's just continue with that. So if you have a spring and this mass m is given a velocity v, it would have a kinetic energy which would given by half mv square. So just anything in motion, even in SHM, a body would have kinetic energy. Now this velocity, as we know from the previous videos, is changing with time. So either we can use this equation, which is a cost function. So because the velocity is a function of time, the kinetic energy also ends up being a function of time. So if I'm just drawing a body executing SHM, so this mass m at mean position. So if you are forgetting what are mean position and extreme position, go back and watch the previous videos. Or just mean position is where the resultant force is 0 and the body has maximum speed. So obviously if the speed is maximum, the kinetic energy would be maximum. And then it reaches an extreme position, and because it has reached extreme, the velocity would become 0, reducing the kinetic energy to 0 as well. And because the kinetic energy is reducing, where is this kinetic energy going? Because any system, if there's no external force acting on the systems, and the only force acting on this m as of now we are assuming is kx minus kx, so minus just shows direction. So the only force acting on this m is a restoring force, which tries to restore it to back to original position. So that means the total energy of this system should remain conserved. And where is this kinetic energy then going? So that kinetic energy would then be transformed into the potential energy of the system. So if we try and draw a graph of kinetic energy, so I'm just taking the graph with displacement. So when the displacement of the body is 0, so body is at 0, the kinetic energy is maximum. So I'm just marking 3 points. And then when my displacement is maximum plus a, the kinetic energy would end up being 0. So this y-axis is kinetic energy. And then if you go on the negative extreme, x is equals to minus a, even here the kinetic energy would be 0. So if you join, then this cannot be joined by a straight line, because kinetic energy is, so because you have the velocity is given by this equation omega, you have this equation in your equation sheet. So as you can see, v is x squared, so it can't be a straight line. If it was an x and v, then it would have been a straight line. So it kind of looked like inverted parabola. This shape here is called parabola. So the kinetic energy is maximum at 0 and minimum at amplitude positions. So then because the kinetic energy is being lost, it is getting converted into the potential energy of the system. So just because the force is now minus kx, restoring force, so the work done by this force would be then a small work. So I'm just writing this as this, and then once you do some area or integration, this is what we get. So the energy, potential energy, would then be half kx squared. And this what is the cause of this potential energy? Every potential energy is always caused by some kind of force. So this potential energy is then caused by the restoring force, and half kx squared. And as we remember, k is mass of the body executing SHM, omega squared. Omega is 2 pi over the time period of oscillation. So the potential energy is, again, as you can see, is directly proportional to x squared. So if my x is 0, my potential energy would then be minimum, or in this case would be 0. So if I draw a graph between potential energy, taking potential energy on y-axis and displacement on x-axis, so when my x is 0, when displacement is 0, the potential energy is also 0. So this is my first cross here. And then when my x is maximum, the maximum possible extension, the potential energy will also become maximum. And potential energy maximum would be half k. Instead of x, you will have now amplitude. The maximum potential energy is half ka squared. So somewhere here. And then even if it is negative displacement minus a, potential energy will also be maximum here because it's a square. So again, because it is proportional to x squared, I'm joining these 3 points by a curve. So this is a parabola, but you don't need to know the name of the shape. So potential energy is half kx squared, 0 at x equals to 0, maximum at x equals to a. But if it is there is no resistive forces acting in the system and total energy of an SHM is conserved, that means there is no losses in any form, there's no deformation, your spring is within its elastic limit, then the total energy of an SHM is conserved, that is Ke plus Pe remains constant. So one decreases, another would increase, but the sum would always remain constant. So if I draw a graph, I'm just drawing the graph where I have, so let's say this is the total energy of SHM. So the total energy would remain constant. So as you can see, I drew a straight line. So even if my displacement was varying along the x-axis, so when x was 0, my energy was still here, x is a, energy is still here, x is minus a, energy is still here. So there's no change of energy, the total energy remains constant. Sometime that energy would be in the form of kinetic energy, like at x equals to 0, there is no potential energy, so all of the energy is in the form of potential energy. So I'm just using a blue color for so here it's only kinetic energy. And when at x equals to a, your Ke would become 0, so blue is Ke. And if I take, let's say, a dark green color, so at x equals to a, then which would come in, so because you have maximum extension, so maximum potential energy, and then this is the position. So the green curve is increasing as the body starts executing SHM, and the blue is decreasing, but the sum of these two would always remain constant, and that would give you the total energy. So the total energy of an SHM in absence of, we are going to introduce friction forces, but as of now, in absence of any friction forces, it is conserved. Okay, any friction or resistive forces or any deformation, there should not be any deformation also, because otherwise your energy of the SHM that was responsible for doing simple harmonic motion, that energy would be lost in deformation. So in absence of friction and deformation, the total energy remains constant. So total energy is conserved. Okay, let's just do some questions on this. So again, try and do them yourself, pause and do it. So this one is asking total energy of the oscillation. So now the total energy could be either, so if you go back to this, so the total energy can be either the maximum PE, the maximum KE, or maximum PE. So whatever. So I'm taking the total energy as maximum PE, and the maximum potential energy is this. So now how do I calculate K? K is m omega squared 12 squared, and amplitude is 0.08 squared using your calculator then. So that is around 0.23 joules. So 0.23 joules. Okay, let's try another one. A particle performs SHM, so this time the amplitude is 0.10, spring constant K. Calculate total energy. So again, calculating total energy from maximum PE, half Ka square. So half 200 times 0.1 squared, that is, I think, 1 joule. Yep. The maximum kinetic energy of the particle will be same as the total energy, so that will also be same. So remember, always remember this graph. Say the maximum PE, the blue part is the Ke, the green part is the PE. So the maximum values of all Ke and PE will always be same. So that would be then the same, 1 joules. So this is the energy that keeps oscillating, sometimes between kinetic energy, sometimes between potential energy. That's the oscillation of energy which happens in an SHM. Okay, so amplitude is 0.2, energy is 1.6. Calculate the potential energy when the displacement is this much. Okay, so now to calculate the potential energy, this is what I need. I need half kx squared. So half K, I don't know. Okay, but I know X. So it is 0.1 squared. This is what I need for potential energy. But how can I calculate K? So I have the value of total energy, which is 1.6. The total energy, I can just use the total energy is half Ka squared. Total energy is 1.6. I don't know K, so using this equation, I can calculate A. Okay, so that gives me K as 80, so writing K as 80, so this is 80 newtons per, K equals 80 newtons per meter, and then using K here, I can calculate U as half times 80 times 0.01, so that is 0.4 joules. Okay, let's do this one. Which statement is correct for SHM energy changes? Ke is maximum at maximum displacement. Obviously not. Maximum displacement means spring is maximum extended. So what should be maximum is the potential energy. Potential energy is 0 at equilibrium position. Yes, potential energy is 0 at equilibrium position. That is kind of right. Total energy decreases. No, it is always constant. Kinetic and potential energies are always equal, not necessary. One might be greater, one might be less. So the second is correct. Okay. So the next one is, now we are introducing forces. So there will be friction forces. Nothing can oscillate forever. So if you push a spring from its mean position, it will start oscillating for some time and then it's going to stop. So such oscillation which cannot continue forever are damped oscillations. Now, who produces this damping? So whenever, now there will be some kind of friction force acting on a system. So whenever there is a friction force, resistive force acting on the system, then the oscillations are said to be damped oscillations. So what is a cause? So the cause is resistive forces, the one who are trying to stop the oscillations. And as it is very much clear, larger speeds would have larger resistive forces. So these oscillations would cause these forces, these oscillations would have then amplitude reducing. They cannot have same amplitude forever. So the amplitude will keep on decreasing. So if okay, so this is one of the type of damped oscillations, which is called underdamped, where this spring mass system will oscillate for some time before it comes to stop. So if I try to draw the amplitude for this one, it will start with the maximum amplitude, and then this amplitude will start decreasing exponentially till it reduces to zero with the help of the resistive forces. Another kind of damping is critical damping, where, as you can see, this needle here is starting going to 120 and coming back immediately. So when the oscillating body comes back to the original position without oscillating at all, immediately it returns back. So this is an immediate returning back. Okay, returning back to original position without oscillating. So you don't want the needle to oscillate. Okay, so whatever speed the vehicle is, the needle should show that vehicle. So you don't want the needle to oscillate. So this is critical damping. There can be something called as over damping. So as you can see in the video, this is a door. The door stopper is trying to bring the door slowly back. So this very slow coming back is over damping. Now, what is the cause of over damping? Obviously, it is very high resistance. So how do we increase this high resistance, or how do we increase the resistive forces? Is somewhere here. There's a thick viscous oil which is producing this huge amount of damping. So over damping is criticized by the slow returning without oscillating again. It does not oscillate. Okay, so the system returns to equilibrium. I'm going to just write here. So system returns to equilibrium slowly. Okay, and obviously because it is returning slowly, the high resistive forces are high. Okay, high resistive forces. Right, now we have done that. Now this damping, after this damping is when you have the resistive forces trying to stop the motion. But sometimes this external forces can also create oscillations, and then if the oscillations are huge in amplitude, as you can see in the video, there's a bridge which is set into oscillations either by wind or it is in this case by wind. So then the amplitude becomes so large and it becomes very dangerous. So what is resonance then? Apart from resistive forces, apart from the resistive forces and the restoring force, so there is resistive forces that causes damping. Then there is restoring forces, that is the cause of your SHM. That is the force responsible for SHM. There's a third force called driving force. Okay, so as you can see in this animation, the driving force in this case is the force produced by the sound of this girl. So the sound is creating this force on the particles of the glass. So if the frequency of the driving force, okay, because the sound is going up and down, whatever frequency she's singing, so that frequency, which we call as driving frequency, if driving frequency becomes equal to the natural frequency, so if you sing or I sing, glass is not going to break, definitely not for me. I don't know about you. So that means my frequency of my sound wave is not matching the natural frequency of the glass. So the glass particles are also vibrating at their own position. So if both the frequency matches, then the glass particles would start vibrating hugely like the particles of this bridge here. So if they're vibrating by a huge amount, then that is called resonance. And what is the cause of resonance? So resonance amplitude becomes very large. Okay. Obviously, the amplitude has become very large in the case of that bridge, or in the case of the particles of the glass, that you can see them. You can see these amplitudes. So what is the cause? Cause is driving frequency becoming equal to the natural frequency. And what's the effect of resonance? Is the amplitude becomes very large. So this is the cause. Taking the right hand cause, and this is the effect of resonance. So resonance is basically just a huge amount of increase in the amplitude. So now let's just see what are resonance curves. Now suppose if I just try and draw a graph between amplitude. So amplitude is on y-axis and frequency is on x-axis, so angular frequency. Now if the driving frequency becomes equal to the natural frequency, so omega 0 here is the natural frequency of whatever is executing SHM. It could be the particles of the bridge or the particles of the glass or whatever is the case. So now if omega and omega naught are equal, amplitude would become very high. Okay, so it's a very high amplitude, or it could be a low amplitude. Now that would depend on the damping. If it is very small damping, then the amplitude would rise hugely at the angular frequency equal to the natural frequency. Okay, if the damping is very high, the amplitude will not be able to rise that much. And at other frequencies, as you can see, the amplitude has come down now. So this has come down now. So the amplitude has come down here. Only at the value of frequencies equal to the natural frequency, the amplitude becomes very high. So this one here is less damping. Okay, so amplitude could rise way high, but if the damping was little higher, it would be, the amplitude will not rise that high. So this is large damping. Sorry about that. So let's just see. So this is how the amplitude and resonance frequency. So the resonance frequency either can be the linear frequency or in terms of omega naught. So this is where, as you can see, if there's no damping, this amplitude is going to go up to infinity. And if the damping is absent, driving force and natural frequency, if they become equal, the amplitude would be so large. And if there is damping, the amplitude of forced oscillation would be less. Now, practical examples of forced oscillations and resonance is these. Go ahead, pause, and they are very common examples. This is especially, I just wanted to talk about the microwave. So whenever you use your microwave oven to heat your food, this is what happens. The microwaves should have the frequency equal to the frequency of the water molecule inside your food, and then because the frequencies are equal, those water molecules starts vibrating at a very large amplitude. So because they're moving at a large amplitude, there will be a lot of collision and the food gets heated through friction. Another examples, so this was also responsible for this tragedy about Tacoma Narrows Bridge. If you want, you can just search on the YouTube, you'll see how that bridge was basically destructed because of the forced oscillation, driving oscillations produced by the wind on that bridge. And the minute it matched the natural frequency of the bridge, amplitude of vibration became very high and it eventually collapsed. Okay, again, pause and try to do the questions yourself. meant by damped oscillation, again ignore this dot, oscillations with which amplitude decreases with time due to energy losses. So that's the answer. State 2 physical causes of damping in a real oscillating system. So if it is a real oscillating system, what is a cause of damping? So one major cause of damping is air resistance. Okay, if you have a spring mass system or a pendulum bob of a pendulum oscillating, the major resistive force acting on is air resistance, and also sometimes there's friction between the materials, okay, or viscous resistance, like that door example that I gave you earlier. So internal friction forces between the bodies, or air resistance, that is responsible for damping. Explain why. So okay, I'm just going to write it here. So one is air resistance. Okay, you can write viscous forces or friction between the bodies. So if a spring mass system is oscillating on a table, the friction between the mass and the table would cause this damping. Explain why the amplitude would decrease with time. Because amplitude is coming because of energy. Energy is continuously being lost to the surrounding as heat or sound. So because the total energy is really, some energy is being lost, total energy cannot remain constant. Say, as energy is being lost as heat or sound. Okay, so obviously the total mechanical energy cannot remain constant. So because total energy is not constant in this case, okay, so because it is not constant, amplitude cannot remain constant. Amplitude, how high it is going to move, it doesn't have energy, how is it going to start moving? State one similarity and two differences between undamped SHM and damped oscillation. So let's see one similarity. Both are oscillatory motions about equilibrium position. Don't say both are SHM, but they both are oscillatory. Differences: undamped has constant amplitude, and in undamped oscillation, total mechanical energy remains conserved. Okay, so I'm just going to write, yeah, let's just write here, or let's just add one slide. Just give me a second. Okay, let's see. So one similarity is both are oscillatory motions. Okay, so both damped or undamped are oscillatory. Don't say they are SHM, because for SHM, the only force acting should be F equals to minus kx, the restoring force. Other forces they start acting, then the motion becomes oscillatory. So undamped and damped, the differences would be in, so if I'm just writing undamped here and damped, so the damped amplitude is not constant, okay, and for undamped amplitude is constant. I'm just going to write the damped, figure out the undamped. So total energy is not constant either, it keeps on decreasing. Okay, a mass spring system oscillates in air and gradually comes to rest. All right, so if it's gradually coming to rest, it is damping. And because it is oscillating sometimes, what kind of damping it is? It is an underdamped system. Explain in terms of energy transfer, where the energy goes, where does the energy goes? If it loses the energy is going to the surrounding as heat or sound. Okay, why the motion eventually stops? Because it ends up losing all of its energy. All of its kinetic energy is lost to the surrounding as heat or sound, so it eventually stops. So yeah, that's it. Then that's it for today. In terms of energy, in terms of resistive forces, or in terms of equations of SHM, if you have any trouble go ahead, revise the videos, and next video I'll try and make on simple pendulum, SHM, simple harmonic motion of simple pendulum. Right, till then, keep revising. Well done. Bye bye. Thank you.